Hello, guys. I'm going to start explaining the characteristics of organic and inorganic matter. Organic and inorganic matter is one of the many classifications you can make of of matter in general, of substances. Okay, and it is a very important classification to understand how living things work and the composition of living things. Okay, so first of all, let us talk about what are organic and inorganic substances by mentioning some simple examples from which you can think of an enormous other amount of examples, yes, by just comparing them. All right. And so, for example, the salt, okay, salt, minerals, as we call them in general, are a very good example of inorganic substances. Water, of course, is one of the most important in terms of the amount of water that exists in the universe, in nature, yes, especially on Earth, right? Metals, okay, steel, iron, aluminum, copper, and alloys, mixtures of metals of different kinds, are very, very typically inorganic substances. But also, stones in general, rocks, okay, are an example of inorganic substances. And grind the stones into tiny, tiny pieces, and then you get sand, okay, which is obviously inorganic. Instead, and by comparison, then we have these are inorganic. Then we have, on the other hand, sugar, right? Sugar. Uh, Here, I mean, I put a picture of hair, yes, but talking about hair, you can compare it not only with other parts of the human body, but also with feathers and nails and horns, or maybe plant materials like wood, okay, are typically organic substances. Okay, now a little bit less related to living organisms, but rubber, okay, latex, right, is an organic substance, the derivatives of petrol, if you wish. Oil, okay, which in this case is clearly olive oil, but other types of oils are also organic materials. Okay, so this is just the examples of organic and inorganic substances for you to picture them. Okay, I mean, the objective of this work is to show you uh, a little bit more visually something that is terribly abstract, okay, that you could study in chemistry with formulas and equations and calculations, but here the idea is try to make it as visual as possible, okay, to be able to understand, to picture it in your mind, okay, when you're talking about organic or inorganic substances. Then, talking about their characteristics and counting on these examples we are talking about, if we refer to inorganic substances, we have a great variety of characteristics. Not only of colors, of textures, hard substances, but at the same time very soft substances, the three states of matter, etc., etc., etc. Instead, although there is a variety of aspects, okay, I mean, if you go back to the pictures, yes, you will see different characteristics. But then, if you put them all together, there is this idea, and think about it, this idea of flexibility. Okay, flexibility. And a second characteristic that is even more important, I would say the most important of all, is that all these organic substances are fuels. They burn, they can catch fire. That means that they contain energy within. Okay, none of the inorganic substances you can use to turn on a fire. Okay, in any case, the other way around, you can use them to put off fire. Okay, and then the place where you obtain them from. Yes, I mean, inorganic substances can be found anywhere. Okay, but anywhere means anywhere in the universe, not only anywhere in Earth. Okay, instead, organic materials are directly related to organisms. Okay, of course, nowadays we can produce artificial organic materials, okay, which is a little bit more difficult with inorganic materials because there is no there is little such thing as inventing inorganic materials because they must have been invented somewhere, only that we haven't found them. Okay. Instead, organic materials, yes, in a way, there is an infinite variety, okay, beyond what living organisms can produce, okay, and this is an important idea. The finding of an organic substance tells you something about the past of organisms. That is, if you find in a certain place some organic material, yes, it means there has been organisms there, or organisms might have been there. All right. Of course, there are a few exceptions to this, but most organic materials are some sort of a print, yes, left by organisms in those places. All right. Then we get to a little bit more abstract content that has to do with the particles. Okay, you know that there is a basic concept in science that was discovered before Christ in Greece. Yes, that all substances, all materials can be parted, yes, can be broken into smaller and smaller and smaller and smaller pieces. You can get smaller and smaller and smaller and smaller pieces of water. You can get smaller and smaller and smaller pieces of a bone. You can get smaller and smaller and smaller and smaller pieces of a paper, etc., etc., etc. Right? This is the idea of particles, that all matter is made of small parts, okay, particles. Now, what about the particles? These particles are what we call molecules, okay. The smallest piece of a substance, the smallest piece of sand is a molecule of sand, the smallest piece of paper is a molecule of paper, okay. And these particles at the same time are made of atoms. And so we can represent a molecule of salt, and we will keep going around the same examples once and again and again. A molecule of salt is made of two atoms, one called sodium, the other one called chlorine. Absolutely curious, if you wish. It's a curiosity only. But then two atoms make up a molecule of salt. Instead, a molecule of water is made of two atoms of hydrogen, yes, and one atom of oxygen. Strictly talking, this space, yeah, when you represent what we call the formula for water, yes, this space shouldn't exist. But I want to show clearly the difference between this atom and this one, okay, and that's why I included to help visually the box, the red box. Then a molecule of sand or a molecule of stone, yes, at least typically on Earth, is made of silicon oxide. That is an atom of silicium and two atoms of oxygen. This substance, this salt, we could call, yes, a natural salt that is called calcium carbonate, is very typically found in water, especially in river water. And so when you see the limey water of the Rio de la Plata or the Paraná, yes, is because it is full of these substances, among others. Of course, there is sand and things of the sort, but also these kind of substances, okay? And among metals, yes, we have many different combinations, but this is the one of the formulas of a type of oxide of iron, okay? Iron is Fe, yes, and oxygen, then it is iron oxide, rust, okay? Well, I insist that this is a simplification. I don't want to complicate the idea with formulas and all that, not yet, but it is to make them visual, because at the same time, compare with the molecule of glucose, referring to the example of sugar we have seen before, right? It's made of 6 atoms of carbon, 12 atoms of hydrogen, and 6 atoms of oxygen, okay? Compared to a molecule of an amino acid like tryptophan that is typically found in hair, okay, or in feathers, yes, or in nails, right? 11 atoms of carbon, 2 of hydrogen, 2 of nitrogen, 2 of oxygen. But let us go on. What about oil? Okay, this There is a type of oil that is called oleic acid, yes, and it has 18 atoms of carbon, 34 atoms of hydrogen, and 2 atoms of oxygen. And then the latex of the eraser, yes, that has modestly 5 atoms of carbon and 8 atoms of hydrogen. What is the conclusion out of this comparison? That inorganic molecules are combinations of any kind of atom, yes, and there are 100 different types of atoms in the universe, in nature, right, that you can see in what we call the periodic table of the elements, yes, and you can combine them in many different ways, okay, and so there is an enormous variety of combinations of atoms of different type. Now, and it's not that I chose among organic substances these four because they were similar. These four are very different organic substances. Sugar is very different to oil, which is very different to hair, let us say, and very different to latex. Yes, but if you take a look, it's only few atoms that are always present. Carbon is always present, hydrogen is always present, oxygen is almost always present, nitrogen every now and then, okay, and a few other atoms like sulfur or other atoms, phosphorus, that appear seldom in these kind of molecules. But at the same time, not only there is few type of atoms, but an enormous number of atoms in each molecule, right? But this is part of the next picture, okay? Because not only there are a lot of atoms, but the atoms are built up into a very complex way. That is, the atom of sodium cannot be complex at all. It's two atoms. The molecule of salt, I mean, cannot be complex at all. It's just two atoms, one next to the other. The molecule of water cannot be so complex. It's three atoms, okay? A bundle of atoms, all of them joined together, okay? And the same with any of these examples. But take a look at the molecule of glucose. Wow. Not only it is made of 24 atoms, but the 24 atoms form a very particular three-dimensional structure. In each of these corners that you can see there is an atom of carbon, okay? 1, 2, 3, 4, 5, and 6, as you had seen before in the other formula, okay? So the molecule of glucose is very complex compared to any of these inorganic substances. Now take a look at the a molecule of tryptophan, this amino acid. By the way, there are 20 different kinds of amino acids. In each of these corners, there is an atom of carbon, again, yes? And hydrogen and nitrogen and oxygen, right? And a double bonding there, a double union and a double union there too. I mean, quite a complexity, right? Complexity that probably you don't understand now, but it's obviously complex compared to just a bundle of 5 atoms together, right? The molecule of oil. In each of these corners, again, there is an atom of carbon and an atom of hydrogen, or 2 atoms of hydrogen, right? Yes, and so carbon, hydrogen, hydrogen, carbon, hydrogen, carbon, and hydrogen, carbon, hydrogen, carbon, hydrogen. I mean, it's not just a bundle of atoms, but it's a complex structure, okay? Each with its own particularity. That's why these 3 substances or these 4 substances are very different substances among organic substances, always with the same type of atom: carbon, 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 I'm sorry, but then carbon, hydrogen, oxygen, yes, you can make a great variety of very complex molecules, okay? So simple molecules are inorganic substances, simple molecules with a few atoms. These are very complex 3D molecules, 3D molecules. Now, what do you think makes all these atoms, these 24 atoms, join in this very particular way? What do you think these many atoms here, I don't actually remember, 17 atoms, if I'm not wrong, join up in this very particular way? How do you think these almost 50 atoms join in this particular way? Do you remember what they had in common? The characteristic all organic substances have in common? Not only that they can make a structure, they burn. and that is because they have an enormous amount of energy within. Okay, the energy that they have within is what makes them have these complex structures. Okay, uh, but not only they are complex, they are super complex, because actually these four organic substances, glucose, oleic acid, tryptophan, or latex, are actually simple units. They are the simplest organic substances. They are among the simplest of all organic substances. That is, they are units that can be joined into much more complex structures that I will show you immediately now. Okay, an example. Not only one molecule of glucose, as you can recognize this hexagon here, you have a chain of molecules of glucose, not only a chain, a branched chain, okay, a chain that is branched here, okay. So many glucose molecules together, that N in mathematics means many molecules of glucose joined together in long chains, we get a molecule of starch, okay. So flour is very much related to sugar, okay. Flour is basically starch chemically, okay, is mostly made of sugar molecules, but of course it cannot have the same characteristics. Okay, starch, flour is not sweet. It doesn't dissolve in water as sugar does. Okay, and that is because it is much more complex than sugar. Okay, here we have one, two, three, four, five, six, seven, eight amino acids, of which one of them is tryptophan, the one I showed you before. Okay, and when many amino acids join together, remember there are 20 different kinds of amino acids. When amino acids join together, many amino acids join together, we form a peptide or polypeptide, okay, which eventually, if there is more than 100 amino acids, I insist, here we have 7, 8, in a protein we have more than 100 amino acids joined together. So imagine the complexity of a protein, okay. A fat molecule is three oleic acids, the molecules that we saw before, yes. Now the three of them join together here, all right. That is what turns into a fat. In this case, it is much simpler because it's only three molecules of fatty acids or oleic acid joined together. And the same happens with latex, that if you join many molecules together, kind of 2,500 molecules of latex together, you get rubber, okay? And that is what the eraser is made of, okay? All these are what we call polymers, and they are the super complex, the macromolecules, okay, among organic substances. And this is the reason why, or this is what our body and the body of all living things, yes, is made up of, okay. Huge organic structures, right, with an enormous amount of energy, which is needed not only to support that structure, but also to supply the energy we need to work, okay. And this is the idea I wanted you to watch, okay. I mean, take the picture, yes, take a view of these type of substances, not just enumerate them or remember them by heart. Try to see their complexity. Thank you for your patience, and I hope this has been useful enough.